Okay. So yesterday, we stopped with the definition of generalized Cartan matrices and affine Cartan matrices. So let me remind you what they are. So GCMs, they were n by n matrices with some restrictions. You needed AII equal to 2, and you needed AIJ to be an integer and less than or equal to 0. And you wanted it to be diagonalizable. That's it. Okay. And then we saw they were of 3 kinds. One was a Cartan matrix, in which case the GCM is positive definite. And then the next was the affine Cartan matrix. Here the GCM is positive semi-definite. And every principal minor is of Cartan matrix type. Proper principal minor is of Cartan matrix. And then the type of Cartan matrix can vary. It could be, it's decomposable, so part of it could be of type D, sometimes it could be of type A, and so on. And then there was the other type, which is called indefinite type, which we are not going to be interested in, about which very little is known. Okay, so the Cartan matrices were associated with simple algebras. Okay. So the affine Cartan matrix should be closely, the corresponding Kac-Moody algebra should be closely related. And the question is, how are they related? Okay. So let's try and do this. And to keep our life simple, we'll work with SL2. If we understand if we understand affine algebras for SL2, we're happy enough. Okay? So for SL2, the Cartan matrix is 2, and one of the affine, so-called affine Cartan matrix, untwisted affine Cartan matrix, won't worry about that, is 2 minus 2 minus 2, 2. So if you remember the other kind, so this is called the untwisted, but people here, like Sachin, work more on the twisted case. So let me just tell you what the twisted case is. Here it'll be 2 minus 4 minus 1, 2. Okay. So these twisted cases are generally very unpleasant to work with. It's easier to work with the untwisted case, so we'll focus on that. Okay. So now I want to describe, the associated Kac-Moody algebra. Of course, we have this Serre presentation, right? So if you're, since this is a 2 by 2 matrix, you have 6 generators, which we call xi, yi, and hi. And here the tradition is to label the nodes 0 and 1. So 1 is sort of the SL2, and then 0 is the additional row and column that you gave yourself. Okay? And they satisfy these relations, so it's worth writing them down once. Again, sorry, Aij, Hiyj is minus Aijyj. Xi bracket yj is 0 if I is not equal to j, and is hi if I is equal to j. And then we had these Serre relations. And a similar one for the y's. Okay. So the breakthrough came when they realized that this algebra could be thought of in a completely different way. Okay. So let me tell you how to do this. For this, we have to introduce the loop algebra of SL2. Okay. So you do something very simple. So let's call it LSL2. So you take SL2 and you extend scalars. SL2 is the complex 2 by 2 trace 0 matrices, And instead of that, you tensor it with a Laurent polynomial ring in a single variable. Okay. So this can be made into a Lie algebra in a very trivial way. You take an element, so let's call it Z in SL2, Z and Z prime, and you take F and F prime. Let's not call that F prime because that's a derivative. So F and G in CTT inverse. And you define the commutator between these two things. So Z tensor F, bracket Z prime tensor G. So you do the most obvious thing possible. You can take the commutator of the two matrices, so you take them. Now, F and G are elements of a commutative ring, so you don't want to take their commutator because their commutator will be 0, so you take the product. Okay. And then it's a trivial checking that this is a Lie algebra structure. Okay. So let us see what these are, if we can define these elements, hi, xi, and so on. Okay. So if you look at this, so remember that you have SL2 as, let's see what I've written over here. So for SL2, you have your Cartan you have your standard basis, which was x, y, and h. Okay. These are relations. Okay. So you can think of SL2 as being embedded inside L of SL2 as a Lie algebra in a trivial way. Namely, you just send Z to Z tensor 1. Okay. So we're never going to write that Z tensor 1 again. We're just going to think of it as a subalgebra. Okay. Now, supposing I decide, so since I said that the generators x1, y1, and h1 live inside SL2, then I just take x1 to be x tensor 1, y1 to be y tensor 1, and h1 to be h tensor 1. Okay. But now I want to produce all these polynomials as well, right? So I need generators which will do that. And it turns out, supposing I take x0 equal to y tensor t, x1 equal to y1, y0 equal to x tensor t inverse. So I don't know what to do with H0, so I'm going to put a question mark. But if I take these 5 elements and I take commutators, then I get the entire Lie algebra. So for instance, if I look at x1 bracket x naught, what is it? It's x bracket y tensor t, right? And what is x bracket y? We know it's h, so this is h tensor t, which I didn't have over there, but now I've produced it by taking commutators. I've generated this element. I can repeat that. So if I do h tensor t now, and I do it with x1, what I get is x tensor t, or 2x tensor t, because the commutator of h and x is 2x, so I've produced x tensor t. So if I do this repeatedly in both directions, I'll produce the entire Lie algebra. Okay? So the summary of this conversation is that these elements generate SL2T, loops into SL2 as a Lie algebra. So I'm able to produce all powers by doing this. Okay. But I still don't know what this element H0 is. Right? So if I looked at this thing, so I want to keep my definition of the Kac-Moody algebra. So let us call this algebra G hat. Okay. So I have a map. So all this is telling me that I have a map, Lie algebra map, from G hat to L of G, which is actually surjective. Okay, map of Lie algebras, which sends x1 to x tensor 1, x0 to y tensor t, etc. But when I look at the commutator and I sent y0, so let's also write that, it sent y0 to x tensor t inverse. And then this will force for me that h0, which is the commutator of x0 and y0, will go to minus H tensor 1. Okay. So there is an extra relation in L of G, which I haven't imposed in G hat. So in this thing, if you look at it, I have H1 equal to H tensor 1, and my H0 is minus H tensor 1. So in here, I have a relation which says H1 plus H0 equal to 0. But this relation has not been imposed over here. So either I have to prove that this relation is forced, right, in which case I have a realization of my algebra, or I have a proper quotient of this. This is a proper quotient of my affine Lie algebra. Okay, so it turns out that, in fact, so the theorem, this is the theorem of Katz, etc. So what we have is a short exact there exists. So if you look at this map G hat to L of G, so L of SL2 in this case, okay, this is a homomorphism of Lie algebras. Its kernel is one-dimensional. Is a short exact sequence. So this is called a central extension. So this is a central extension. Short. I should write one thing at a time. Okay. So this is a short exact sequence. This is a central extension. G hat is a central extension of L of SL2. This would be a boring central extension if the sequence was split, right? It would mean you didn't really need the trivial. So it's in fact a non-split central extension. Okay. And moreover, it's also the universal central extension. So if you had any other central extension, then this would split off. Okay. So this is the theorem. This is a theorem due to I don't remember. Let's just attribute it to Katz. Okay. So the Katz-Moody algebra is a one-dimensional central extension of the loop algebra of SL2, and it's completely explicit. And I just have to tell you now, so let us then, so this is the missing element H0, okay? So this is the theorem. Yep, so I'm taking, so now, right. So over here, you see, so now I've got my G hat. So this theorem is telling me that I have this direct sum. This is only a direct sum of vector spaces, not as Lie algebras, right? Because this is a non-split short exact sequence. So I'm not going to split this off as Lie algebras, but I am going to write it as a direct sum of vector spaces. And I have to tell you what the commutator in this algebra is. Yeah? So this is a central element. What is a central element? It's one which commutes with everything. So I have C bracket L of G. Commutes, and the bracket operation here is the operator. So C bracket LG is 0. And then I have to tell you what the relation between two things in LG is. Right? Now, obviously, it has to change. It can't be what it used to be, right? Because then the center doesn't play a role. And the way it becomes, so the first term is unchanged. It's exactly what it used to be in the loop algebra. But now I add a correction term. Okay? And the correction, well, where is the correction term going to lie? It's obviously going to lie in the center. That's subspace. And what is the correction by? You take, these are matrices, so you can take their trace. You take the product of the trace. And unless R plus S is 0, you don't get a correction. And if R plus S is 0, then you get a correction by the multiple of the center. In other words, you have a non-trivial cocycle that gives you the central extension. Okay, so this is how this Lie algebra is defined. Okay. So as you can see, when you look at this Lie algebra, you can see SL2 totally obviously, and all the relation and all the structure is very easily defined. There is no mystery in it. Okay. All right. And what is this center? Remember, so over here we have this H0, H1 plus H0 equal to 0. So H1 plus H0 has to lie in my kernel. So the center is actually just C of H1 plus H0. So it commutes with everything. So this is the definition of the affine Lie algebra. Okay. So, yeah. Okay, so then one moves on to wanting to, so we're basically doing representation theory of affine algebras. And one moves on to asking ourselves, what can we say about the representations? Yeah.
I'm sorry, G hat is basically that algebra
with
relations.
Yeah, exactly.
We have started with SL2 or some any general G.
No, here I started with SL2. That's why I only have 6 generators.
Oh, okay.
If I had, but this definition will work, I just need more, I'll just take 3 n generators. Okay, so moving on to representation theory, of course, you want to ask yourself what kind of representations should you study? They should be somehow manageable representations. So what do we study when, yeah?
So for the general G, what will be the generator for the center?
That's right. So the generator for the center, okay, so let me do, so if you're doing SLN, right, or SLN plus 1, you know Lie algebras, right? So it'll be, so the center will be H naught plus H theta, where theta is the long root of SLN plus 1. So you remember how I constructed the affine Cartan matrix in that case, right? I took the usual Cartan, I'm always talking about the untwisted case. I took the usual Cartan matrix and then I added a row and column which came from the long root. And the negative of it. So when you go to the dual thing, you do H theta. Yeah. Okay. Right. Are there any other questions? Okay, so when you're doing a course on representation theory, the first course, whether it's groups or Lie algebras, you study finite dimensional representations, right? When you study finite groups, you study finite dimensional representations as well. Okay, so we want to maybe do that here as well. Okay. Now we know that due to this theorem of Hermann-Weyl, we know that finite dimensional representations in a semi-simple Lie algebra are isomorphic to a direct sum of irreducible representations. So we can say, okay, let's study finite dimensional representations of affine Lie algebras. And so that's one way to put it, right? What is the other way to put it? So if you look at finite dimensional so given a Lie algebra, you always have a Lie group associated with it, classically. So what are finite dimensional representations? They lift to the corresponding Lie group, right? They integrate to the corresponding Lie group. This is because some operators act locally nilpotently and you can lift them, taking the exponential action. That's how you lift the Lie group. Okay. So instead of saying, let's just look at finite dimensional representations, you could work with this idea that you want to lift it to the corresponding group. There is a notion of a loop group. It's much more difficult to work with, but you could just ask whether you can lift it to that loop group. So then the language becomes slightly different. You want to talk about lift. So let me just say, so this is sort of not formally correct, but if you have a map from G to G, right, and you have a representation from G to endomorphisms of V, right, then you sort of want to lift one of these generators to the corresponding group, right? And so you want to make sense of x of rho of xi. This is in principle an infinite sum, so if you want it to make sense as an operator, you need it to be zero, you need the powers to be zero for all but finitely many elements, right? So that motivated the definition of an integrable representation. So that's the more general concept than finite. So let me first say that. So an integrable representation. Okay. So you want the torus, or in this case the elements hi, okay, I equal to 0 to n, to act semi-simply or diagonally on the representation. Okay. So that means you can write V as a direct sum of eigenspaces for the HI, for the action of the HIs. Okay. So this mu is just a collection of mu naught integers, not, well, scalars. So let's just say in C to begin with. Okay. So that's one condition. And then there's the condition of local nilpotence, which will allow me to lift my operators. So that is that the elements xi and yi act locally nilpotently on V. So nilpotent means the fixed power kills the entire vector space. Locally nilpotent means that for every vector there's some integer which will kill it, right? So for all V, in V, there exists some integer r depending on V such that xi power r equal to 0 equal to yi power r on V. Okay? The r can vary with the V. Okay. So this is the definition. How does it match up with SL2 representations? Okay. So this can be, let's not just do SL2. This is for any semi-simple Lie algebra, simple Lie algebra. Integrable representations of a simple Lie algebra are nothing but direct sums of finite dimensional representations. Okay, so this definition then is a good analog of finite dimensional representations. Okay, because it covers, so this is nothing new in the case of simple Lie algebras. You're just getting the old finite dimensional representations. But in principle, when you're doing it for affine, you don't know what you're getting. So imposing the restriction of finite dimensional is too much. So sometimes you have to look at different ways of thinking of finite dimensional representations. So then it turned out that that was the definition that Katz gave of integrable highest weight representations. So. And of course, any finite dimensional representation is integrable once you want the things to act semi-simply. So integrable implies finite dimensional, and we'll see that the converse, so integrable for affine, does not imply finite dimensional. We'll see that in a second. It's a trivial example, and the converse is, of course, trivially true. Okay, converse is trivial. Okay, so we never move ahead without examples, so let us look at examples. Okay, let's look at this concrete example of representation which has lots of so what is the most canonical representation of a Lie algebra, of any Lie algebra? They all come equipped with one representation, and that's it, right? And what is that one? Sorry? That's the adjoint representation. So let us look. So if you have a Lie algebra G, you always have the adjoint representation, which is G acting on endomorphisms of G, and it's given by add x on y is equal to x bracket y. So this is the adjoint. And you always know the adjoint representation and sometimes nothing else. So let's look at what the adjoint representation of the Katz-Moody algebra is. Yeah. No. See, what this will mean, so if you take integrable representations of simple Lie algebras, every element will lie in a finite dimensional module. So it will become a sum of finite dimensional modules, and then because of Weyl's theorem, it will become a direct sum of irreducible modules. So you don't need to assume. Okay. Okay, so I want to investigate the adjoint representation so I'll stick with SL2, right, of G hat. And so let me remind you, so G hat is this L of SL2, direct sum the trivial. right? So, and this bracket G hat is 0 because it's the center, right? So this is a submodule, right? And G hat by C is, so this is a submodule under the adjoint action. Yeah, so I'm thinking of G hat acting on itself through the adjoint. Okay. So the adjoint, so of course for a simple algebra, you used to the adjoint action being. I'm doing G hat associated to SL2. Yeah, I mean, it's just so that I can avoid introducing too much notation. So okay. So C is this is the trivial. So this is the center. So the center acts trivially, right? So that means the center is a submodule, right, of my G hat. Okay. So CC is a submodule. Okay. And remember, I told you that this is, and so this is the quotient module G hat by C, and of course we know that this is isomorphic to L of G, right? So what does this statement, and then I told you that we have the short exact sequence, non-split short exact sequence, which looks like this. So what is this telling you? What does this example already tell you? The fact that this is non-split, it tells you something. So it tells you that this representation is indecomposable, right? You have, so anyway, so we'll come back to this. I want to make a point over here. And now let's study let's study this LG. Okay? So we have these elements X tensor F, right? And now supposing so X, Y, H is my standard basis. So if I look at add X tensor F, no, I only have to look at add X tensor 1, right? Power R. Then you'll agree that this is 0 on Z tensor F for all Z and F, will you? Because how does this act? X tensor 1, this will just be add X power R on Z tensor F, right? And of course, the adjoint representation of SL2 is nilpotent, right? I mean, these are the upper triangular matrices, and these act the powers are 0. Okay, so this is 0. And then you can calculate in the same way that the other things are 0. So if you do add Y tensor T power R on Z tensor F, how is this going to act? If you do it repeatedly, what you will get is add Y power R acting on Z tensor T power R F. But this is still 0. So I'm done, right? So this is an example. So LG is an example of an integrable representation, right? So now what have I got here? I've got G hat, the adjoint representation. It contains the trivial representation. It maps onto an integrable representation. So it's integrable on its own, but it's not a direct sum of anything. So complete reducibility fails almost immediately, right? You don't need to look very far, and you should never have to look very far to find an example like this, right? So complete reducibility or Wiles theorem fails immediately. Even if this is not a completely reducible module, but even if it was, it fails. Okay. This also gives you an example of an infinite dimensional integrable representation. So it also tells you that converse, it's not just that I don't know how to prove that integrable representations are finite dimensional. This is definitely false. Okay? So this is the adjoint action. So the adjoint action tells you immediately that you have to do more theory. Yeah. Do you have a question? No. Okay. Are there any questions?
Why HIs are called diagonal?
Because for SLN plus 1, so there are many Cartans about, well, let's not introduce language. So in SLN plus 1, the HIs, right, it's most convenient to think of them as, one can think of them as diagonal matrices. I mean, they're a basis for the diagonal matrices. So, I mean, typically when you're doing semi-simple algebras, what you'll find is that there is a collection of elements which are act diagonalizable. That means they act diagonally on the Lie algebra, and they're so then you can prove that they're commutable.
So that sub-algebra in some sense that maximal abelian.
Yeah, exactly. It's a maximal total.
Operator algebra, we have this Cartan.
Exactly. So this is the So basically, you should. I mean, ideally, I should be working with an arbitrary simple Lie algebra and a Cartan subalgebra, but I don't want to. All that becomes terribly abstract. So I want to work with a concrete example, which is SLN, and a concrete example of a Cartan subalgebra, which is the diagonals. But of course, you can replace them by conjugacy. No, that also I will give you examples now. Yeah.
This example also gives saying that
That's right. Yeah. So this is an example of a non-trivial extension. Yeah, in the category. Exactly. Yeah.
not true for simple.
Exactly. Yeah. That complete reducibility is the same as saying that there are no extensions, and here this is giving you almost trivially an extension. Are there any other?
You said jihad was a universal set of extension. In what sense?
I think it means that if you have any other extension, it'll factor through. This will factor through. Okay. Are there any other questions before I? Okay. So. Okay. So yeah. So I've given you, so when I said equally clearly, I've given you an example now of infinite dimensional integrable representations. I've explained to you, I haven't proved for you that this is irreducible, but it's not very hard to do. And I've shown you, well, okay. And I've shown you that complete reducibility fails, okay? And then, okay. Okay, so now we, okay, so now I've defined integrable representations, and I've decided that that's the correct analog of finite dimensional representations to study, right? So we're going to focus on integrable representations. And as always, when you're working in the infinite dimensional setup, you have to impose some finiteness conditions. So if you remember, I had this V equal to direct sum V mu, where these V mu's were eigenspaces for the H action. Okay. And so we'll always impose the condition that dimension of V mu is finite. You need some structure to make your subject work, at least to begin with.
They may not have any integrable representation.
I just gave you an example. The adjoint representation was integrable.
Oh, okay. Sorry.
So that's why you start with that. Yeah. Okay. So, yeah. And then an obvious question is, can you classify it? So what do you want to classify? So, of course, you would really like to classify indecomposable representations, right? But this one knows is generally a wild problem. I mean, you can't usually do such things. So you start with, so the first thing you want to do is to classify at least the irreducible integrable representations. And then what else do you want to do? And then after that, for the rest of your working life, what do you do, right? So once you've done this classification, then you have to, once you're in what's the point of being in a non-semi-simple category if you restrict your attention to irreducible representations? You want to study questions of extensions or indecomposable modules in some way, right? So that's what I'm sort of going to talk about next. So let's talk about these irreducible integrable representations, okay? So for that, we need to recall some elementary things. So So let's remember, so we have this V mu, and let's remember that we have the center, which in the case of SL2 is H naught plus H1, right? More generally, H naught plus H theta, okay? The center is in the span of these things, right? It's in the span of H naught and H1. So the center, of course, acts on V mu by just...
Remember, H naught plus H is 0.
No, it's 0 in LG.
Oh, yes.
It was the center in, it was a non-zero center in G hat. Okay? So see, a V mu will act as mu naught plus mu 1. Right? So it acts as a... So now, of course, you all know Schur's lemma, but let me formulate it here for you. So this V is, so now I'm assuming that V is irreducible, integrable, etc. Right? And let me take an element, a non-zero element in some V mu. Right? Certainly, I must have some mu such that V mu is non-zero, so I'll take an element in that. What does it mean to say that it's irreducible? In particular, it means that it's generated by these elements, by the element V. So what does that mean? That means V is obtained by repeatedly applying things like X tensor F1, Y tensor G2, whatever, right? H tensor G3, and you just keep applying it. Take the span of the subspace generated by all these things, applying arbitrary numbers of things like this, okay? Now, so now if you calculate C on this element, right, what does it do? Well, C just commutes with all these things. So it goes over and you get C on V, right? And so you get, and then the C on V we knew was just mu naught plus mu 1. And we get that, right? So how do you summarize this? What you've proved is that C acts on this irreducible, so this is Schur's lemma, C acts on V by a scalar multiple of the identity because it's irreducible. Okay, so what can the scalar multiple be? Okay. So let's go back and look over here. So V is an integrable representation, right? And remember that we have this xi, yi, and hi for each I. And this is, well, this is a copy of SL2. So this is a copy of SL2 whether or not I'm in SL2, right? Because this is just for every Chevalier generator. Okay, this is a copy of SL2. And these elements act locally nilpotently on V, right? So in particular, this V is an integrable representation for SL2, right? So it's a direct sum of irreducible representations for SL2. Okay? So what one knows, I think actually I have a slide a bit later. Yeah, that's right. So it's a direct sum of, so now what one knows is that for irreducible representations of SL2, all the eigenvalues of H, all the eigenvalues of the diagonal elements, so of HI, must be an integer. So although here I've written that the mu i's were complex numbers to begin with, because I'm in the case of integrable modules, these mu i's are all actually Z. Okay. So what I've proved is that this scalar multiple is actually an integer scalar multiple. Okay. So this integer is called the central charge of V. So this is just some language. This language was borrowed, of course, from the physicists. A long time ago. Okay. It's also known as the level of V. So this is the central charge. Okay. Okay, so this is just what I explained. This is just what I calculated for you. And so here we are. So I've proved now that the center must be a scalar multiple of the identity. Well, integer scalar multiple of the identity. So there are immediately three choices, right? The center can be positive, negative, or this integer can be positive, negative, or 0. Okay. So let's just answer the question, what is the central charge of the adjoint representation then? It's just in a different language. So what is the central charge of the adjoint representation? The central charge is just, if the center acts by a scalar on a representation, then you call it the central charge. So the central charge of the adjoint representation, well, the center commuted with everything, so it was 0. So of course this is 0. Okay. So we know an example where the central charge is 0. Okay. So now I want to so what is the obvious triality, as I said? So you can have the center is a positive integer, or you could have that the center is a negative integer, or you could have c equal to 0. Okay? So these are called positive level representations, etc. And level 0. Okay. So I haven't given you an example of positive level representations. That requires more definitions and so on still. And I might be unable to avoid notation. But I've given you an example of this. We can construct more examples of these easily. But before we do that, what this is telling is you can break up your study of integrable representations into 3 categories, where the center acts positively, the center acts negatively. So if you have any integrable representation, you can write it as a sum of 3 pieces. So what we've chosen there. So V plus, direct sum V0, direct sum V minus. So the center acts by different positive things here, 0 and negative things. Okay. So this separates the study of integrable representations into 3 categories. And actually, as you can perhaps imagine, there should be some symmetry. So if you understand positive level representations, then you should also really in some sense understand integrable level representations. And in fact, you can do that by an automorphism of the Lie algebra. So you can apply some automorphism which will turn a positive level to a negative level integrable representation. So in effect, one only studies positive level and 0. And their behavior is completely different. Okay. Okay. So, yeah. I'm sorry, say that again? No, because I think the center will separate it, yeah. Yeah, so as I'm going to explain, if you work in this category V plus, where the central charge is always positive, that's actually a semi-simple category. So any representation is a direct sum of irreducible representations. This is not true in the case of V0, and then you do have extensions, but the blocks are very big, which is a bit of a problem. Yeah. So it's not like, I don't know if you're familiar with category O, but there you can restrain it with the while group, but here the blocks are very big. But yeah, you can construct the blocks. They are in fact so they are indexed by the weight lattice modulo the root lattice. So there are very few blocks. So very often P is equal to Q, and so that in fact the whole thing is one block. Yeah, so it becomes a very tedious. So the natural, some of those natural ideas don't work, okay, which is a problem. So that's why you always have to do a workaround. other. Okay. Yeah.
So is there any connection of these with the G representation? We started with the algebra G.
Yeah.
And this is G hat. So V plus V0, are these related to any G representation?
So we're going to see that for V0 they are, okay, and that for V plus they will break up as, so you'll have branching rules. So what I mean, yeah. So if you take a representation in V plus, you can regard it as a module for G. Then you could ask what representations occur over that.
But these are not like, G does not give the complete information.
Oh no. Yeah. You need more in both cases. Yeah. Mm-hmm. This will be like if you work with, so one more often works with the Heck algebra and the affine Heck algebra, and then the Heck algebra you know something, but affine won't give you all the information. So, okay, so we go back to SL2. So what are all the representations of SL2? There's the obvious one, which is the trivial. Everything acts as 0, okay. At the group level, everything would act as the identity. And then there's a natural two-dimensional one, right? If you have...
Sure, V plus is coming from that, first we started with V and that C is acting on V.
Yeah.
That constant of the action may not be same for all V.
Yeah, so if it's not irreducible, yeah, the constant might not be same for all V. And if it's...
And we are collecting all that, that if the constant is positive, we're collecting those.
Exactly. Exactly. You're just separating those things, and then you're going to only study things with...
But C was acting on some particular spanning subspace, not on V. So V acting before some X plus Y.
So C was acting on the whole thing, right? But I started by picking one vector on which it acted. But because it's a V, I did the thing for irreducible, so I'm being a bit sloppy. I did the thing for irreducible, so that was enough, right? And then after that, so I should have been more precise. So then what you can do is you can write V just as a module for C, right? And then you can just write this as direct sum Vn, right? Where Vn will be all the elements V in V, such that Cv equal to Nv, right? Then this will be a G hat submodule. Okay? So remember, C is an element of my Cartan, so it acts diagonally. So I'm just collecting the eigenvalue of that fixed element. And then I can write V plus will be all those things Vn with n greater than 0. V minus. Yeah? Okay. Yeah. So for SL2, we have this obvious representation, two-dimensional one, right? So you can just make SL2 act on endomorphisms of C2. The matrix A goes to multiplication, right? And how do you construct? So this is like if you were starting with the symmetric group, then you have the canonical action, permutation action, right? And that contains trivial, and then you can get the other action. And how do you construct? What's the standard way to construct more examples of representations? You take tensor products, right? So if you take tensor products, well, we know one more example, which is the adjoint. Because you're working with a simple algebra, you have an irreducible one. And I don't really want to write these down, but anyway, so for Vn, so now so I've got a one-dimensional, two-dimensional, and a three-dimensional representations, okay? And if you write it down carefully, what you'll see is that you have a basis that you can find actually an n-dimensional representation, right? And if you, such that n plus 1, sorry. And you can write down the action of the SL2 on it. So it'll be something like this. It's not too important. So I might have got these scalars wrong, but it's not important. The main point is it's a string-like behavior. The H's preserve each of these things. X's map each of these things up like this, and the Y's map everything down like this. And there are some scalars that you have to be careful about to make it an action. Okay? And then again, the standard result first result in representation theory you prove is that these are all the irreducible finite dimensional representations. And so it's usual to denote these by Vn. Okay? So this is just, so I don't really have the time to do it in greater detail, but this is what we're going to do. Okay. Okay. So another way, so this is one way, you write it down completely explicitly, right? But you know, really, if you go beyond SL2, you know you can't do explicit things. So what you do is write down a presentation. So the presentation in the case of SL2 is that it's generated by an element which has eigenvalue n for the H action, which is killed by X, okay, and a sufficiently high power of Y kills it, local nilpotence for that element. Okay. And then you can prove that this module is irreducible and has dimension n+1 and is given in this way. Okay, in the higher rank case, how do you modify this? So, so the higher rank case, you don't expect to write down anything like this, so explicit. So you just give a presentation. So if you take G to be arbitrary simple, then there exists a non-zero element V in V. So, sorry. And you take mu to be a collection of positive integers, not positive, non-negative integers. Okay. Then V mu, so this is a finite dimensional module. So it's generated by, so an element V, such V mu, let's say, with the relations Hi of V mu, so it has to transform according to the mu I. The Xi's all have to kill it. Okay, and the Yi raised to mu I plus 1, V mu is equal to 0. All I'm doing is taking whatever I wrote down for SL2 and doing this now for higher rank, for every SL2 inside my simple Lie algebra. Okay?
Xi powers?
No, Xi. For SL2, I had, so I'm just taking that and I'm putting in a subscript I for everything. Okay? This is the standard result. And one proves that, so it turns out, so when you look at this statement, you can see immediately what statement to formulate for an affine Lie algebra. Because what's the difference between an affine Lie algebra and a simple Lie algebra? I have one extra node, right? So I can replace this mu by mu equal to mu. So for the affine case, I replace that mu by mu naught up to mu n, right? And here I was in 1 up to n. And here I is in naught up to n. So this is all, this is all Katz did in the beginning. He looked at the presentation of an irreducible module for a simple Lie algebra and did the obvious modification for the affine Lie algebra. So where does the difficulty come in? You can define anything you like. The difficulty comes in proving that it has all the nice things that you want. But then the theorem that was proved, so, and let me make a comment over here. If you remember that our H for SL2 was H1 plus H naught, right? Again, SL2, not HC, was H1 plus H naught, right? And how is this going to act on this vector? It's going to act as mu1 plus mu naught, which is now going to be greater than 0 unless they're both 0. So this is a positive level representation. If this is a nice module, this is a positive level integrable representation. So then the theorem that I want to state, which is perhaps a good point to stop, theorem. So supposing we take G hat to be the Kac-Moody algebra. Okay. So this can be stated, so there's nothing special about, so once you come to this point, there is nothing special about it being affine. You can just define it for any Kac-Moody Lie algebra. So you can take that to be the Kac-Moody algebra with the Chevalier generators. Okay. Let's say I equal to, I'll continue to call it I equal to naught up to n then, and let mu be any collection of non-negative integers. And this is not the zero vector. Right? Then there exists a unique irreducible integrable representation, which is necessarily of positive level, and corresponding to mu. So the definition is the presentation v mu, and it's given by the preceding presentation. So the exact analog of, as I said, this is the exact analog of the statement that one proves in a first course in semi-simple algebras, that it just goes through for Kac-Moody algebras. So we have lots of positive level representations, therefore. This is what this shows. Not lots, a discrete number, so I want to be careful. So you have a discrete number of representations, positive level representations, and then the next part of this theorem is any positive level integrable representation is completely reducible. Okay. So in this part of the category, the positive level part of the category is what's called to be semi-simple, right? And so there are other interesting problems that you can study about these modules. What is their character, and what are the tensor product rules, branching rules. But the only objects of interest in the category are the irreducible ones. All extensions are zero, so there is nothing further in the categorical structure to study. Okay.
This true for arbitrary capital?
Symmetrizable, I only think of symmetrizable. Diagonalizable. Yeah, this is, yeah. Yeah. Okay, so I think this is a good place to stop. So tomorrow I will finish up by talking about level 0 representations and the difference in the two theories. So thank you for your attention.
Question? Here we don't have any role of L of G. Can we extend this representation to over L of G?
So L of G is a quotient, right?
Oh, yes.
So, and the center is acting non-trivially, so it's not going to factor through. But when the center acts, so it's a good point, when the center acts trivially, this becomes unimportant, and we're really going to only be looking at representations of L of G. So that's
what is the importance of L of G?
and
to understand the representation.
So if you want to understand level 0 representations of this, then you understand these representations instead. That is the role, right? And then, as I said, I mean, the real interest in this comes from the fact that it's not semi-simple. So the irreducible representations are not so interesting in some sense. But because there are interesting extensions and so on, the category structure is very rich. So that's why one wants to study this. Irreducible is indecomposable. Yeah, so do you mean that given an irreducible representation, do I have an indecomposable representation? Exactly, yeah. So that is exactly true. It's so that's what I want to explain tomorrow. So tomorrow I want to explain that I have what the irreducible representations are, show you that they are not indecomposed. Yeah, and show you that for every one of those things, you have an associated indecomposable module. And then there are also finite groups, and so there are also projective modules and things like that. So it's a question of how to develop that theory. So it never goes perfectly. But all those ideas are what are being explored here. Yeah. Yeah, that's what I want. Oh, yeah. So those things, everything is context dependent. So, so sometimes, so the BGG resolution, which happens, for instance, for semi-simple Lie algebras, right? That's between, that's a resolution of the finite dimensional module by projective modules and so on. You have problems, so there you have to go to a bigger category, right? You don't work inside finite dimensional. So here also you have to go to a bigger category, but the question is how big, and yeah. So those are the kinds of questions that one is exploring in this whole thing. And in between there are digressions with different, so as I said, the methods don't always work, because in the case of Lie algebras, many of these things are proved by using block decompositions and knowing extensions. But those, because here the blocks are so big, they don't work.
What is the reference for this thing?
Sorry?
What is the reference for
This
this?
will be in Katz's book, Infinite Dimensional Lie algebras.
And when it has been proved?
70 something, 80 something.
Very old.
It's an old result. Yeah, it's essentially the first result that people proved in the subject, right? Because it's all just imitates what was proved for simple Lie algebras. So.
There are no further